Just take a look around you for a second. Chances are you are surrounded by concrete. I mean, it's the most common man-made material on Earth. But today, we're going to talk about an invisible upgrade that's making it stronger, safer, and way more durable than ever before.
You know, we think of concrete as this permanent, unshakable symbol of strength. But what if that strength has a breaking point? What if the very structures that define our cities are actually vulnerable to these slow, relentless attacks that they were never really designed to handle?
Because, well, they are. For all its incredible strength, traditional concrete has some major enemies. You've got tiny cracks that can grow into huge problems. The steel rebar inside, it can rust and expand, basically breaking the concrete apart from the inside out. Intense fire can literally make it explode, and in cold climates, something as simple as water freezing and thawing can just tear it apart over time. But what if the solution wasn't some crazy, radical reinvention, but just a simple, brilliant tweak to the concrete mix itself? Well, that's exactly what we're going to dive into. Say hello to fiber-reinforced concrete, or FRC. The whole idea is actually incredibly simple. You take your normal concrete mix and you add in thousands and thousands of tiny little fibers. These can be made of steel, glass, or synthetic stuff. It's a really small change, but it has a massive impact. So, how does this actually work? Well, think of all those fibers as a 3D microscopic rebar network that's woven all throughout the concrete. The moment a tiny, microscopic crack starts to form under stress, bam, it immediately runs into a fiber. And that fiber acts like a bridge, holding the concrete together and stopping that tiny little flaw from turning into a complete disaster. So with that one fundamental upgrade, FRC is now uniquely equipped to fight back against those enemies we just talked about. Let's get into how this material actually survives the attack. Okay, take what happens in a fire. Usually, the moisture inside concrete turns to steam and builds up this immense pressure. This can cause the surface to just violently explode. It's a thing called spalling. But as recent research from Jiang and others shows, if you've added polypropylene fibers, they melt at a pretty low temperature. And when they melt, they create this network of tiny escape channels. The steam gets out safely and the whole structure stays intact. It's genius. So what about corrosion? You know, the rust that just destroys so much of our infrastructure? Well, because FRC is so good at controlling cracks, it dramatically limits how much salt and water can even get to the steel rebar inside. And get this, some researchers, like Almasaba, are even using steel fibers from recycled tires, which not only makes the concrete greener, but actually improves its corrosion resistance. How cool is that? And for those chilly climates, the logic is just as elegant. When water seeps into a microcrack and freezes, it expands and pushes the crack wider. The next time it thaws and refreezes, it gets even bigger. But in FRC, you've got these fibers that are literally acting as bridges, physically holding the crack together and stopping the ice from forcing it apart. It stops the damage before it even has a chance to build up. Okay. These claims all sound pretty impressive. But in the world of engineering, claims are not enough. You absolutely need proof. So how do scientists put this material through the ultimate stress test? Right, this is the critical question. How do we go from a really great idea in a lab to a material we can trust for our most important structures? How do we know it's really as good as it sounds? Well, they tackle it from two different angles at the same time. The first is physical testing. You know, actually making real samples of FRC and then bending them, breaking them, and putting them under incredible stress to see what happens. The second path is digital simulation, where they build these virtual models of the concrete to test thousands of scenarios that would be just impossible to do in the real world. In the lab, these tests are pretty intense. Like, as Kafaji and Azawi showed back in 2023, they use these massive machines to simulate earthquake forces on joints. They do push-off tests to see how well a new layer of FRC bonds to old concrete. They bend beams until they fail just to measure their toughness. And with amazing tools like digital image correlation, they can literally watch and measure, pixel by pixel, how cracks form and how the fibers jump in to stop them. And at the same time, you've got these incredibly powerful computer models running. These simulations can predict exactly how a beam will bend or where a crack is going to form. This lets scientists test countless variations, different fiber types, lengths, amounts, to find the absolute perfect recipe, all before a single bag of cement is even mixed. So, when you combine the real-world results from all those physical tests with the incredible predictive power of the digital models, the conclusion is just undeniable. fiber-reinforced concrete delivers on its promise. We're talking definitive proof of enhanced durability, strength, and resilience. The proof is there.
All right, so we have a stronger, more durable material, and it's been proven by science. But what does this actually mean for us, for our world? Why does this innovation really, truly matter? The payoff here is huge, and it really comes down to three big things. First, we get safer structures, buildings and bridges that are way better at withstanding fires and earthquakes. Second, we get longer-lasting infrastructure that can actually fight back against decay. And all of that leads to a more sustainable world. Because, think about it, a bridge that lasts 100 years instead of 50 means we spend half the resources building and rebuilding our world.
And that really brings us to a final thought. Concrete is literally the foundation of our modern world. If an idea as simple as just adding tiny fibers can improve it so fundamentally, it really makes you wonder, what other essential things are out there just waiting for their own invisible upgrade? What else can we reinvent right from the inside out?